set up this proof, 0, 0, 2?
So I started with assume that x is odd and y is odd. Then there exists an m and n that are integers such that x equals 2n plus 1 and y equals 2n plus 1.
Okay.
So then I said also assume that the product xy is even.
Okay. Assume x, y is even. So, given those two assumptions on the table, what method of proof is she setting up to use here? What kind of a proof is this setting up to be?
Contradiction.
It's a proof by contradiction. How can you tell?
Because the premise, the P is still the same, but the Q is inverse.
Right. And we're assuming them both. So we're taking them both on the table. P is true, Q is false. So we're setting up a proof by contradiction here. And that means that the goal is then to show that there is some other statement out there in the logical universe that, as a result of both of these statements being assumed to be the case, must be both true and false. And since in formal logic statements cannot be both true and false, our original presumption must have been wrong. Okay, so then where did it go from here?
So from there I just said that there was a k, so that xy equals 2k. So
Okay.
it's even.
Xy is equal to 2 times k for some k, for some integer k. And I also didn't get to a chance to write down how you used the oddness. You said x was equal to
2m plus 1.
2m plus 1, y
2n.
2n plus 1, where m and n are, okay. All right, so this text in brown is what we get from our assumptions. Again, it's a lot to work with. We can say something about x, we can say something about y, and we can say something about xy. Okay? So that's a lot of material that gives us. Okay, then what happened?
Then xy equals 2n plus 1 times 2n plus 1.
Okay. But then xy, according to our first assumption on the top, is the product of 2m plus 1 and 2n plus 1. All right.
And then if you do all that out, you get that xy equals 2 times 2mn plus n plus n.
You get 2 times 2mn plus n, and then there's a plus 1 here, right?
Yep.
Okay.
So then I said let k equal 2mn plus n plus n, so then xy would equal 2k plus 1.
Probably don't want to use k here, but I'll buy that.
Or L, yeah.
Yeah, or L. By the way, why do I need to use L here instead of k?
It was very easy.
Yeah, we use k for something else. 2mn plus m plus n. Okay, and so what does that tell us about xy?
Therefore xy is odd.
But isn't xy already equal to 2k? Like, couldn't we say that?
Okay, right. So this was going to be my point about this. So we just did some algebra based on the hypothesis that p was true, that showed us that xy must have the form 2l plus 1 for some integer n. Right? Then, on the other hand, if we want to make this a proof by contradiction, we not only, so maybe let me pause here for a second and finish this proof in a way that I would have an issue with. So we might say right here, if xy is equal to 2l plus 1, we might say, hence, what do we know about xy? It being 2l plus 1, xy must be odd. Okay, but then what's my problem with finishing the proof that way?
Is it because we're assuming that xy is even, so we're saying xy is equal to 2k, so if we just said hence xy is odd, like we need to compare the two? Is that what you're saying?
In a sense, yeah. If we just jump straight to hence xy is odd, we never used anywhere the assumption that q is false, right? And if we didn't use the assumption that q is false, then arriving at this statement, xy is odd, that's the statement that q is true. And so what did we do? We assumed p was true. We made another assumption we didn't use. And then we deduced just from the truth of p, the truth of q. What kind of proof is that? That's a direct proof. Right? So it's very easy to to think that you're doing a proof by contradiction or think that you're doing an indirect proof, when really, at the end of what you have written down, because you haven't falsified something else, right? Instead, we end up falsifying the assumption that Q was false without ever using the assumption that Q was false. So we didn't need the assumption that Q was false in there in the first place. And we had a direct proof. This is the time for us to talk about this. It's not as big of an issue down the line, but I think that it's important to, when we're looking at proof structures, to think about that. So is there a different way that I could finish this proof that will actually use the assumption that Q is false, that XY is even? Does anybody see a way that we could continue it and get there?
So can you not just say, therefore, 2L plus 1 does not equal 2K?
Well, we can't say that it doesn't equal 2K, but we might be able to deduce that it doesn't. Let's figure out how. So we have up here one characterization of XY as being 2L plus 1, and a second characterization of XY that came from our assumption that XY was equal to 2K. So how do we get those two things together? According to our work, 2K is equal to 2L plus 1. Right? Let's see if we can go from there and figure out something to contradict. What can I do with this? What do we know about K and L? They're integers. So why is 2K equals 2L plus 1 a problem if K and L are integers? Yeah, Claude.
Because an L can't equal anything.
Well, do we know that? I think that might be something we're about to prove. I agree with you. That is exactly what where we're going. So how could we get there? How could I turn this equation into something that looks patently false? Or a contradiction to something we know to be true? What if I get the k's and the l's on the same side of the equation? If they're both integers, let's try and get them together. So I'm going to subtract 2l from both sides. And there I'll get 2 times the quantity k minus l is equal to 1. Okay. Does that get us any closer? What do we know about k minus l? So the left-hand side, yeah, the left-hand side is even. That's true. The right-hand side is still odd, but we still haven't really proven that it even can equal an odd. Yeah.
2 divided by 2 and then say that the difference of two integers can't be a fraction.
That's where I think I'm going with this. Yeah. So we know k minus l is an integer. But if I divide both sides by 2, and by the way, dividing is kind of a scary thing in number theory. And if you're taking 303 or have taken it in the past, you don't do a lot of dividing in that class because it's not always a well-defined operation. But if we just do that for now, we don't need to be super sophisticated about our number theory in this class. We'll say k minus l equals 1/2. But k minus l is an integer. Right? And so here's a statement, k minus l is an integer, that has a corresponding statement, k minus l is equal to 1/2, which it contradicts. Because 1/2 is not an integer. There is no integer which, when you multiply it by 2, you get 1. Right? So, in a way, we could say because k minus l is equal to 1/2, that implies that k minus l is not an integer. And so it followed from our algebra that k minus l was not an integer, but it followed from the other stuff that we did that because k and l were integers, their difference also must be an integer. So what do we have? We have r and the opposite of r that would both have to be true as a result of assuming that p was true and q was false. So that might be a proof by contradiction of this statement. We started by assuming a lot. We assumed p is true and q is false. And then by doing the work that proceeded from both of those assumptions, so we had to use both of those assumptions along the way in order for this legitimately to be a contradiction proof. But when we use both of those assumptions, we end up with a statement that's not sustainable. We end up with a logical proposition that is therefore both true and false, and that is what logicians call a contradiction. Since it's not possible to have a statement be both true and false, that means that our original set of assumptions cannot be sustained. In other words, our trip through the looking glass to a world where this theorem is not true is something we can't do. And if our theorem can't be false, our theorem must be true.